Everything we know, from the billions of people on Earth to the hundreds of billions of planets in our galaxy to the trillions of galaxies, is a lot of matter. But did you know that this only consists of around 5% of the universe? So what about the remaining 95%? Part of the answer is dark matter. Galaxies seem to be achieving the impossible as they rotate with such a speed that the observable matter could not generate enough force to hold them all together. This led scientists to believe something we cannot see is at work. The idea of dark matter may have started in 1884, when Lord Kelvin said in a talk that many of our stars, perhaps a great majority of them, may be dark bodies. Lord Kelvin had come to this conclusion due to the orbital speeds of stars and galaxies. This is still one of the main pieces of evidence for dark matter. Our observations of spiral galaxies by using electromagnetic radiation suggest that most of the matter in a galaxy is clustered in the center. When most of the mass of a galaxy is clustered in the center, a single star's orbital velocity can be approximated to depend only on the mass of the center of the galaxy and the distance from the star to the center. Therefore, the orbital velocities of stars should decrease as their orbits get further away from the center. This is not what is observed. Instead, the orbital speeds stay close to constant as one moves away from the center. This indicates that either our understanding of gravity is wrong, or that there's a lot of mass in the universe that we are unable to observe. Dark matter.
Since the first concrete hypothesis of dark matter made by Vera Rubin in the 1970s from her observations of the velocities of sections of stars at the edges of spiral galaxies, there have been mainly three contenders for its explanation. The first theory is that dark matter is made from particles we already know about. However, by studying gravitational lensing, the bending of light from a distant galaxy by a large mass in between the distant galaxy and us, and comparing that to our observations of the large mass that is causing the lensing, shows us that there's nowhere near enough mass from regular particles to account for the amount of lensing observed, so this theory is already out of the running. The second theory is that general relativity needs modification, which implies that our best theory of gravity, general relativity, doesn't work on the massive scales of galaxies and clusters of galaxies. It therefore needs modification to account for the observed effects such as the orbital speeds of stars and galaxies. However, a new theory of gravity would also have to explain the many independent observations that support the existence of dark matter, not to mention match up with general relativity on the things we already understand. One example of this are observations of galaxy cluster collisions that strongly indicate that dark matter must be made of particles, and a modification to general relativity wouldn't explain that. The third theory, and the best contender at the moment, may arise from supersymmetry, a theory that predicts more massive counterparts to the particles we already know. These particles, often called WIMPs, meaning weakly interacting massive particles, would be way more massive than regular particles and are predicted not to interact through electromagnetism. These then are the perfect candidates for dark matter. However, there's no experimental evidence to back this theory. It is just a mathematical solution. The search for dark matter continues, which now brings us to 2017. At the forefront of dark matter research, scientists have created the most sensitive dark matter detector ever, Xenon 1T, which is a very large vat of liquid xenon. The scientists will try to use this experiment to gain evidence for the existence of WIMPs, which are predicted to only interact very weakly with the nucleus of regular matter atoms through the weak force. Physicists are hoping that the WIMPs will hit the liquid xenon nuclei, producing light particles, or knocking off an electron that could then be detected. Unfortunately, the Xenon 1T so far has proved to be fruitless, but scientists aren't losing hope just yet.
Perhaps in the future, as technology develops, we will gain further insight into this elusive, which